Hello, everyone. Today we're going to talk about Chapter 6. Chapter 6 is about discrete probability distributions. We have two sections for this chapter. We're going to start with the random variables and then define distribution. And further, we're going to talk about the mean standard deviation of a random variable. And then we're going to talk about this special type of discrete distribution, which is called binomial distribution. So now let's start with section 6.1, random variables. So let's recall variable. A variable was defined as a characteristic or attribute that can assume different values. So we always use capital letter X, Y, or Z to represent variables. Since the variable in this chapter are associated with probability, so they call a random variable. So what is a random variable? A random variable is a variable whose values are determined by chance. So if we can present possible values for some variable and the possible values corresponding chance or probability, then we have a random variable. And then we're gonna further look at discrete random variable along with the discrete probability distribution and continuous random variable along with the continuous probability distribution. So let's look at an example. The example for discrete random variable. Let X be the number of classes a student will miss in a semester. Then X could be 0, 1, 2, 3, 4, 5, 6. And for each one, they have a corresponding chance or probability. So the probability of no missing at all is different than the probability of miss one class. So this is example for a discrete random variable. And why we say it's discrete? Because a discrete random variable is a random variable whose possible value can be listed. So we can list the value out. And then in particular, a random variable with only a finite number of possible values. For this one, we have just 0, 1, 2, 3, 4, 5, 6. And then let's look at this practice. Determine whether the following random variable is discrete. Let the capital letter Y be the possible number of rolling a single die ones. So this is some example we've been talking in the last chapter, rolling a single die once. Then we know the possible values could be 1, 2, 3, 4, 5, and 6. So the possible value can be listed. And then for each one, we can have a corresponding, we can look at the corresponding chance. So to get a 1 is 1 over 6, 2, 1 over 6, and so on for a fire die. Then this is a discrete random variable. And for this Z, representing the height in meters of randomly selected maple tree, height is a continuous variable because you can have any number from a range, so it cannot be listed. Then we say this is continuous random variable, and then we're going to talk about continuous random variable in the next chapter. So this is not a discrete one. Then we're going to look at discrete probability distribution. So a discrete probability distribution is just present the random variable possible values and the corresponding probability. And for the probability histogram, is just like the histogram we see from previous chapters, and then the y-axis is representing the probability or the chance. And then let's look at further look at discrete probability distribution. It can be shown by using a graph or a table, or a formula. So these are the ways that we can represent a discrete probability distribution. But we'll focus more on the table one. For example, probability distribution and histogram of the random variable x, which is the number of siblings of a randomly selected student. So possible values we can have is 0, 1, 2, 3, 4, just up to 4. And we don't consider for more than 4, or we don't observe it. And then the corresponding probabilities are listed. And then this is a table that representing this random variable. So we say this is a distribution, or we say it's a discrete probability distribution. So again, it's very similar to the frequency distribution. When you have a frequency table, then you have a corresponding frequency histogram. Then same thing, when we have this table, which is the discrete probability distribution, then we're going to have a corresponding histogram, which is the probability histogram. So for 0, we have 20%. And then for 1, we have 42.5% chance. So this height of the bar representing the probability of that value happen. So two requirements for probability distribution. The first one is the sum of the probabilities of all the events in the sample space must equal 1. That is, sum of px equals 1. So if we look at the previous example, so sum of all the probability equals 1, because that's the probability of sample space. And the probability of each one in the sample space must be between or equal to between 0 and 1 or equal to 0 and 1. So we have 0 smaller than the probability of x smaller than 1. So now let's look at a practice problem. We're going to construct a discrete probability distribution for hats received after tossing a coin twice. So then let's look at the sample space. Again, for tossing a coin twice, we have head, 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 tail, tail, head, and tail, tail. And now we want a discrete distribution for heads received after tossing a coin twice. So from the first outcome, we have 2 heads. And then for the second one, head and tail, we have 1. And then we have 1, we have 0. So 2, 1, 1, 0. The possible value that has received will be 0, 1, 2. So if we use x to represent that random variable of hats received after tossing a coin twice, we could have no hat, which is 0, 1 hat, and 2 hats. And we're going to write down the probability of all the corresponding values. For 0, you have just 1 outcome out of the 4 outcomes in the sample space. So that's 1 over 4. For 1, you have 2 ones. So 2 over 4. And then for 2, you have 1 over 4. Then let's check whether sum of those equals 1. So sum 1 over 4, 2 over 4, 1 over 4, which is 1. So no problem, verified. And it is a discrete probability distribution. So interpret of probability distribution. In a large number of independent observations of a random variable x, the proportion of times each possible value occurs will approximate the probability distribution of x, or equivalently, the proportion histogram will approximate the probability histogram for x. And same thing, so when we calculate this discrete probability distribution, we use the theoretical version of the probability formula. So and this is the distribution, theoretical distribution. And if we want to interpret this probability distribution and why we say the probability of observing zero has going to be 1/4, we can repeatedly do this experiment. So tossing a coin twice, and then we can just write down the number of the experiment. So for example, we got a 0, and then toss a coin twice, and then all tails. So we got a 0, write it down, and then we repeat the same experiment again. And then we make out a 1, and then a 0, and a 1, and a 1, and a 1, and a 2, and a 0, and a 1, so on and so forth. So you will see the result will be limited to this 0, 1, and 2 after you do the same experiment. Let's say you do 400 times. So you're going to have 400 numbers in this data set. And then you can make a frequency distribution. And then it's going to be 0, 1, 2 as x, and then the frequency. So you will observe about 100 0, and then 200 ones and 100 twos. And then if you use empirical probability to calculate that, it will be very close to the theoretical probability we put here. So that's the interpretation of a probability distribution. And then we can look at the mean of a random variable. So let's recall the GPA example, how to calculate a weighted mean. Then we have mu equals, okay, let's just kind of review this real quick. So mu equals sum of x over n. So for English class, GPA is A, and 4 hours, that means for A you got 4.0, B 3.0, A 4.0, B 3.0, C that's a 2.0, and 1.0. So for 4.0, 4 hours means you got 4 of those. So we can rewrite to 4, and then another A, so another 4/4, and then 3, the hours 3, that means you got 3.0, and then 1 hour of A, so 1 4.0, and then 3, and then 2, and then 1. So we can just write back this transcript by weight. At the weight. And then we know we have a total of 20 hours, so that the total numbers we can have, then that's n. So then 4/4, that's 4 times 4. So all the red colors represent the weight or hours, and then we have a total of 20 hours, no problem. And then for each one, you can, because this is a sum in the numerator and then with a common denominator 20, so you can rewrite it to 4 times 4 divided by 20 plus 4 times 4 divided by 20, and then 3 divided by 20. So 4 divided by 20, exactly, that is exactly how much weight this English class in the whole semester. The whole semester you take 20 hours, for example, and then English is a 4-hour class. Then 4 divided by 20, that's the weight for this English. So basically your GPA times the weight. So we can rewrite in this format. So now we know the weight is the probability, right? So probability of English, probability of math, probability of stats. And then to make it a formula, we're gonna say that's the sum of x times probability of x, the corresponding probability. Then we say the mean of a random variable with a discrete probability distribution, gonna be using this notation mu of a random variable x. So mu of x. And then we have each possible value times the corresponding probability. So sum of x times the probabilities. And then you take the product of the value and the corresponding probability first, and then take sum. So this means the sum of the products. Another name for the mean of a random variable, we call it expected value. Just a different symbol, expected value. So E of x, we call it expected value. So the mean of x equals the expected value equals sum of x times the probability of x equals all given numbers. So this lowercase x represent all possible values there. And then we can look at this example. Toss a coin 3 times and let x be the number of hats produced and calculate the mean. So the discrete distribution of x is as follows. Then we can just calculate the mean using the formula. Expected value of x, or we say the mean of x equals sum of x times probability of x. So take product of each pair and then take sum. So the first value we have is 0 times the corresponding probability, which is 0.125, plus the second value you have there, which is 1 times 0.375, and plus 2, the next value, times 0.375, and plus 3 times 0.125. So we got, so 0 times anything that's 0. So we got a 3 over 8 plus 6 over 8 and plus 3 over 8. Because this is 0.125, that's 1 over 8, and times 3, that's 3 over 8. So we got 3 plus 6 plus 3, so 12 over 8. So that's 1.5. 1.5. That's the expected value or the mean of this random variable x. And now let's look at the interpretation of the mean of a random variable. So in a large number of independent observations of a random variable x, the average value of those observations will approximately equal the mean mu of x. The larger the number of observations, the closer the average tends to be mu. Then we can do this experiment. Toss a coin 3 times and let x be the number of hats produced. So first toss a coin 3 times and then count the number of hats. And then do the second time, the third, until 100 times. So we have all the following values, so which is a real experiment. So for the first one, out of 3 tosses, you got 1 hat. So you just write down 1. And then for the second one, out of 3 toes, you got 1 hat. So you just write down 1. Until the fourth time, you got 2 hats out of the 3 toes. And then you just keep writing down all those, and then we can make a frequency distribution. So this is the different class, because we have 0, 1, 2, 3, all the only numbers we have. So this is actually single value grouping, and then this is a frequency. This row. So we got 17 zeros, 36 37 twos, and then 10 threes. And then the mean, the weighted mean of all these we can calculate, which is 1.4. That's the weighted mean. Weighted mean. And then the theoretical mean we calculated already, which is 1.5. So when you do 100 times of this experiment, the observed calculated weighted mean will be already very close to the theoretical 1.5. But what about you do 10,000 times? Then we can repeatedly do this and then calculate the mean. the mean is 1.4917. So that is very close to the theoretical value already. What about keep increasing? We do 1 million replications, then the mean is exactly 1.500711. So that's exactly 1.5 already. So that's the interpretation of the mean of a random variable. And then again, it's the law of large numbers. The law of large numbers. We mentioned that before. Okay, so for this video lecture, we'll just stop here, and then next one we'll start with the variance and standard deviation of a discrete random variable. Thank you.